So for the final talk of the session, we will have Thomas telling us about cohomology rings and cubical agda.
Hi, so today we're going to do stuff properly this time. So I'm going to explain how to compute cohomology rings in Cubical Agda, but mostly I will explain how data structures influence formalization. So first of all, what are cohomology and cohomology rings? Well, a question that you may have is how can I prove that two topological spaces are not isomorphic? And if you fix a bit the Klein bottle and the Mickey Mouse space, you can kind of intuitively see that those spaces are not isomorphic as topological spaces. And still, it's quite hard to come up with a mathematical argument of why. And so that's why we invented cohomology and cohomology groups. The point is that to each topological space X, we're going to associate a sequence of abelian group Hi of X, named the cohomology groups, such that they are invariant. If two cohomology groups are not isomorphic as groups, the topological space won't be isomorphic as topological space. And the point is that those groups are supposed to be easy to compute and relatively nice, like Z or Z times Z. So you can actually compute them and compare them to prove that topological spaces are not isomorphic as topological spaces. In particular, we're going to work in synthetic mathematics and Homotopy Type Theory. And what is nice is that cohomology has a relatively nice and short definition. So it's not really important for the rest of the talk. But what's important to understand is that it actually enables us to compute indeed nicely and quickly a bunch of examples. So let's look at examples. Well, on the left, you have a bunch of classical topological spaces. And you can see that indeed, by computing cohomology groups, you can prove that they're not isomorphic. For instance, the Klein bottle is not isomorphic to the circle because H2 is different. It's not isomorphic either to the real projective plane, nor the complex projective plane, nor the Mickey Mouse space. Each and every single time, thanks to cohomology groups. So already we've answered a bit to the first question, how can we prove that topological spaces are not isomorphic? But are cohomology groups enough? Well, they are not. You have some spaces that are not isomorphic, but have the same cohomology groups. And for instance, you can see CP2 and S4 wedge S2 that have the same cohomology groups but are not isomorphic. And so what can we do? Well, something nice is that cohomology groups relate to each other. If you take them all together, they have more structure. There's an operation, the cup product, that is a graded operation. It goes from Hi to Hg to H over I plus G. That enables to give more structure to the groups. And indeed, if you gather all the groups into direct sum, then you can give to it a ring structure using the cup product. And this is called the cohomology ring. And something that's really nice about this cohomology ring is that it gives you one more invariant. If two cohomology rings are not isomorphic as a ring, then the topological space won't be isomorphic. And so, for instance, it does enable to tell more spaces apart because CP2 and S4 wedge S2, even though they have the same cohomology groups, have different cohomology ring. So what is our objective? Our objective is to prove some ring isomorphism, characterize some cohomology ring. So basically, it means that we want to prove that the cohomology ring, which is a direct sum of the cohomology groups, is isomorphic as a ring to a polynomial ring with several variables quotiented by finitely generated ideals. So what are the issues? Well, first, we need a good direct sum. We need to be able to define cohomology ring on it. So we're going to generalize this to graded rings because it's always easier to work abstractly. Secondly, we need a practical definition of multivariate polynomials because we're going to define map in and out to prove an equivalence. And for that, we need a definition that's practical because otherwise we would have to always deal with a lot of bureaucracy. And lastly, we need to prove ring isomorphism. So in particular, we need to prove that the functions respect the product. And so we will need a product that is nice enough to handle to actually do proof with it. And this is very important because we're working in Cubical Agda. So a constraint is that we don't have any tactic. So if we have a definition that is too bureaucratic, we can't use tactics to help us. We have to do all the work ourselves. Another constraint is that working in synthetic mathematics, everything in constructive. So we would like to keep it constructive, and we're going to stick to that, especially as usually being constructive leads to better definitions. So let's try to build a direct sum and the notion of graded rings. Well, let's try the simple thing. Let's try to adapt the classical set definition. If you do that, well, the classical definition is just saying that elements in the direct sum are the sequences that are null except in a finite support. So you can translate this directly into type theory. You just follow the regular guidelines. So you had sigma types, p types. You had proposition truncation because you don't want to add more structure. And well, this could work, except you need the notion of finite subset. And the notion of finite subset does not behave well in constructive mathematics. There is two concurrent definitions, Krotowski finiteness and Bishop finiteness. And the issue is that both of them require more properties on I. It requires the index to have either menocidable equality or decidable equality. And so in the general case, you won't be able to prove that this definition verifies the universal property of the direct sum. So it's annoying. However, we only want to take the index in the direct sum to be n, so we can just like restrict ourselves to that. And in this case, we get a nice definition because n has a nice subset, so you can just say that the elements are the sequences that cancels after a point. Well, if you do that, let's try to build a ring on that. Well, given two sequences, you can just like add them pointwise, and you get a nice abelian group structure. There's nothing much to say on this. So let's try to define a product. So let's generalize a bit to graded ring. Let's just consider a general graded operation over the usual monoid. Well, basically, we want the product, as for the polynomials, to just be all the elements that can be decomposed in g of I and g of g. And so it just gives us the regular sum, or the convolution product. And this would be very nice, but if you try to type this in a proof assistant, it won't type check. Because actually, in intentional type theory, like homotopy type theory, MLTT, and so on, g of I plus n minus I is only equal to g of n up to a pass. It's only equal propositionally, not definitionally. And so because of that, you won't type check. And so to make it work, you need to add transport. So if you do that, you get to a definition that basically works. But if you try to prove any properties about it, it's going to be really annoying. So that's associativity, basically. So as for the polynomials, you get sums. You need to swap sums. You need to change index. But now you even have transport to handle, and you need to change index in the transport. So it's going to be awful. And every time we will have to prove a ring isomorphism, we'll need to prove that it's preserved product, and we're going to end up on this. And remember that this is a very simplified case. We're taking the index to be n, and not a general notion with general subset. So can we do better? Well, we could try to follow a more type theoretical approach and use inductive type. And because we want to do mathematics, we're going to use quotient inductive types. So it gives this big definition that can be a bit scary at first, but it's actually quite easy. So the most important constructor is the base constructor. Basically, it takes something in I, so in an index, a coefficient in g of n, and it gives you an element in the direct sum. So basically, you can just think of base as the sequences that have zeros everywhere except in the nth position, which has a coefficient that may be null or not. Then you want an abelian group structure, so you add a 0, you add a plus, and you add the usual law, associativity, right identity, and commutativity. Then you kind of want base to be a morphism, because you want to prove a universal property of direct sum. And basically it makes sense, because if you have the sequence that has, for instance, zeros everywhere except in n, and in n you have 0, indeed it's the 0 of the group. And same if you get two sequences that match in n, you can just add them inside the group. Finally, you add set truncation, because we're working in homotopy type theory, so you can have more structure. But basically, it's just a quotient inductive type. It's not a higher inductive type. So with this nice definition, we have an easy way to think about it. We can just think that this is the object that is generated by the sequences that have zeros everywhere except in one place. And you can just think about that. And that's really nice because it's actually how it behaves. For instance, let's try to define a product as we were doing before. So let's be even more general than before. Let's take a general monoid, a general graded operation over the monoid to get graded rings. Well, we can define a product by double recursion. And it's going to be very easy because in the 0 or the plus case, it's trivial because in a ring, 0 cancels multiplication and it distributes over plus. If you're in the base case, well, you can just multiply x and y in the base case, and then you get in base of n plus m. And then you get the different equations of the quotients to verify, but all of them are going to be completely straightforward. And so what's very nice with this definition is that we've dropped notion of sums, we dropped transport, everything is nice and by recursion, and compared to the classical direct sum, it may be a bit bureaucratic, but everything that's bureaucratic is in a few lines and completely straightforward. You don't have to think about it. All the equations that you have to prove, basically, they are like in 3 lines. So let's try to prove associativity that was L before. Well, we can just use triple induction for each argument in the definition of associativity. 0 and plus are going to be automatic. The base case and false to this definition. Basically, you just swap the parentheses. So it's like a dependent application of a base. And this is just an hypothesis of what it means to be a graded operation. So everything works out fine. And finally, all equations of the quotient are trivial because you're doing mathematics in a set. And so all the equations are already verified. So basically, proving associativity ends up in 10 lines, and you have almost nothing to do. And so with this new definition, you see that defining the notion of graded rings is very straightforward and much more general as before. We don't need finite subset. We don't need assumption like I as decidable equality or stuff like this. Everything is straightforward. And so it gives us a good definition of graded rings. And in particular, if you instantiate I with n and star with the cup product, you get the definition of the cohomology ring. But there is even more to that. Once that we have the direct sum, we can define the polynomial as just saying the direct sum over n of the ring. And for the graded operation, well, there's no type dependency here. So you can just take the product of the ring. But you can be even more general and like define n variable polynomials. You just change the index to be n power n. And this definition is perfect for what we want to do, prove ring isomorphism, because if you've noticed now, the cohomology ring H star and the polynomial are defined the same way with one direct sum. So when you're going to define a function in and out, you won't need to change data structure. So you will avoid all the bureaucracy that you could have found otherwise. Moreover, you have a direct definition of multivariate polynomials. It's not defined by iteration, as it is in many textbooks. So you can directly handle multivariable polynomials. And it's really practical. Elements and product are intuitive. The elements are basically 0, ax power n, which is base. It's how you think about it in mathematics, and a plus. And the product is just basically generated by the usual law of a ring and the usual multiplication over the powers. And so basically we find something that is perfect for our purpose. Now we have something that gives us a good definition of cohomology ring, a good definition of multivariate polynomials, and a good definition of the product. So now we're going to be able to define and prove the ring isomorphisms. So let's just look at an example and consider a general method on that. So first, we're going to define a function from the polynomial ring to H star, the cohomology ring. We can use this by recursion. Everything is recursion induction now. Prove that C is a ring morphism. Again, you can do it by induction for each of the cases. To get a ring morphism on the quotient, well, something nice that you can just prove it cancels on the generators, and you're going to get a ring morphism on the quotient. And then building an inverse, you can just do this by recursion, and you're going to be able to prove it's a left and right inverse, again by recursion. So what's the input of the data structure here? Well, building the psi function is very direct, because you have direct sum on each side, so you just need to map the different group of each direct sum in the good groups in the other side. Proving it's a ring morphism, well, the only non-trivial case is that psi respects the product, and that's very direct, because using induction, it unfolds to proving that psi respects the cup product just on the power. Then proving that psi cancels on the different element in the quotient, well, if you build psi correctly, it should be by definition, so you have nothing to do. And building an inverse is equally direct, and proving it is equally direct. And so basically, using the good data structure, all that we need to prove is what we care about. All that we need to prove is characterize the cohomology groups and characterize the behavior of the cup product on the space. And that's what this equation means. And so data structure is really important for what we want to do here. And something that is nice is that now that we have unfolded all of this bureaucracy work, we can really use synthetic mathematics and homotopy type theory, because in homotopy type theory, spaces and functions can be defined by induction. And so you get a short and more graspable definition of cohomology, as given in the introduction, well, in my opinion at least. But also you can define the cup product directly by recursion. You don't need an involved definition like the smash product. It's just an induction. Combined with the fact that you can directly manipulate paths synthetically in a cubical Agda, well, it will give you a simple and short computation of many cohomology groups, as we've seen in the table at the beginning. But moreover, you're going to be able to prove that the cup product is indeed a graded operator, and you're also going to be able to characterize this behavior on spaces. And for instance, characterizing the behavior for the Klein bottle is basically taking 10 lines. So it's really efficient. So to conclude, basically, by using an appropriate definition of the direct sum for a purpose, we've built the cohomology ring, and we have also explained a new definition of multivariate polynomials that enables to directly manipulate powers. Moreover, we explain an informal general method to compute cohomology rings. But what is most important, we've shown that data representation really influences formalization, and by using a good data representation, especially quotient inductive type, you can actually really ease your work. So in the paper, you will find a bit more stuff, mostly on direct sum, graded rings, and polynomials. You will also find a data refinement problem, for once not in computer science, but in mathematics. And you will find a different computation. So what we've done here in the talk is just Z cohomology. So we'll find different computation for that on a bunch of examples. But we have also formalized the G cohomology ring, and we have computed the two examples, so the Klein bottle and RP2 S1 in Cubical Agda. So thanks for listening, and do you have any questions? Well, that's something that's interesting. If you take Z coefficient, you have an example here. The Klein bottle and RP2 S1 have the same Z cohomology ring, but different Z mod 2 cohomology ring, and that's why we computed them. In the general case, the answer is supposed to be yes, but I don't know any simple example because I mean I'm more a computer scientist. I'm not a specialist of algebraic topology.
Another example would be the Homotopy would be without the spectrum of I heard you say the word induction, reduction. Are you using the
No, I was just saying that. Yeah.
Any more questions? This is not a question, but it's a comment. This is actually another one of our distinguished paper awards, and sort of for IMAT. But congratulations. You will receive your certificate in this meeting, so please make sure to stay a while.
Well, I think if that's all, let's have a break maybe.